Alright, we're gonna do a recap of everything so far. So, here we go. I'm gonna go through some concepts that we've done, view a couple of equations, theories, some results from labs, but just a quick summary of all the topics that we've done so far. So, there's really only two giant overarching ideas here, and the first one is kinematics. So all kinematics is describing motion. So saying where something is, how fast is it going, how long did it take to get there, and how much did it accelerate. So we're answering those four questions here: position, velocity, acceleration, and time. And we had a couple of equations. So this first one here is only for something at a constant velocity. So if there's no acceleration at all, then we can calculate its velocity by doing the position over the time. If something's accelerating, then it's a bit more complicated. So we've got our three main equations here. These are all just for word problems, and essentially just a math puzzle. So you have all but one variable, and you just have to solve for that other variable. And so the three equations that we use for anything that's accelerating are these. And we haven't done a lot of calculus yet. We will later in the year. But so far, we have only done two equations, where velocity is just the derivative of position with respect to time, and then acceleration is just the derivative again. So it's the derivative of the derivative. So we saw this a little bit in kinematics, and the times where you would use these in particular is if you had some equation of motion that isn't, you're not really given initial velocity, final velocity, you're just given an equation. So if it was something like 4t squared, and I asked, okay, what's the velocity at certain times, what's the acceleration at certain times, you would just use the two equations and find derivatives. So the other big topic is dynamics. So in comparison to kinematics, dynamics is describing why stuff moves. Before, all we did was describe how it moves, and this one we're describing why it moves. So we have three laws that describe this motion of anything. And so one by one, these are Newton's laws. So Newton's first, second, and third laws. So the first one was something that you know probably already, and it was an object at rest stays at rest, and an object in motion stays in motion unless there is a net force acting on it. So what happens if there's a net force? Well, this is what it is right here. So if there's a net force, it equals the mass times the acceleration. So for the first law, F net equals 0. Second law, okay, what if the velocity is not constant, or what if it's not at rest? Then we describe it like this: mass times acceleration. Third law is equal and opposite forces. So this is whenever one object exerts a force on another object, that other object exerts the same force back, and it's negative. Okay, where all this comes from is always from a force diagram. So we've got two cases: one where the net force is 0, or 2, or not 1 and 2, A and B. So situation A is the net force is 0. Situation B is when it's not 0. Okay, so this is an example for A. So if the net force is 0, then all of the forces will balance each other. So everything will cancel with something. If the object is accelerating, then one of the forces is bigger than the other. So in this case, we've got a net force to the left. And so we'll have to use our mass times acceleration equation for that. Alright, so how do the two big ideas relate? How does kinematics relate to dynamics? So one is describing how stuff moves, and the other one describes why stuff moves. So I'm going to show you with an example. So Everything comes from this, mass times acceleration. Let's say the net force acting on an object was 10 newtons, and that object had a mass of 5 kilograms. Let's say it was something that started at rest, and then this force was acted on it, so it starts to accelerate. So my question is, how much does it accelerate? Well, it's really easy. It's just 10 divided by 5, so we get 2 meters per second. This is where it relates back to kinematics. We now have an acceleration, and we said that it starts from rest. So we can do all the same calculations we did before, like find out how far it goes or how fast is it going. So let's do that really quick, just as a quick review. So those are the things we know. So we found its acceleration. We said it starts at rest. And let's say I want to answer some questions about around 8 seconds. So how far is it in 8 seconds, and how fast is it going at 8 seconds? Well, this is pretty straightforward. These are just using those equations that we had before. So we just use the equation with 1/2 at squared because it starts at rest and it starts at 0. So it's just 1/2 at squared, and that will tell us how far it goes. And if we want to know how fast it's going, then we can just use this equation, where that is 0. So it's just going to be a times t. Alright, so a summary of what kind of forces we've got. So there are generally 4 forces that we're going to look at pretty much all year. Alright, and that's tension, friction, gravity, and the normal force. So when do we know which one's which? So if there's a rope or a chain or a string or something pulling on something else, then that's tension. If 2 surfaces are rubbing against each other, so the block sliding across the table, slamming your brakes in the car, and the tires skid, that's when 2 surfaces rub together, so that's going to be a friction. Gravity is easy. It's just the earth pulling down on an object, so that is almost always going to be in your force diagram. And then the normal force is when 2 surfaces push on each other. Alright, so let's compare the normal and friction really quick. So we've got a block on a hill here. If we draw our force diagram, it's going to look like that. So we got gravity down, normal is perpendicular to the surface, and friction is parallel. So this is the notation. You may remember this from math, where the normal force right here, that means perpendicular, and then for friction that means parallel. So for any surface, the normal force is always perpendicular, and for any surface, the friction is always parallel to the surface. If that's true, then that means the normal force is always 90 degrees from friction. No matter what, every single situation, that will be true. So whether it's on a wall, it's on a ceiling, it's on the floor, if it's on a hill, normal force and friction force always form a 90-degree angle with each other. Alright, so here are the last couple of applications that we talked about when it came to forces. And the first one was spring constant. So the spring constant K, that was what we got from our graph of force of the spring versus displacement. It was the slope of that line. So that slope right there tells you how stiff the spring is. So if it had a very high number, then that means that spring was a very strong spring, and if it was a low number, then that means it was a stretchy spring. The other one that we recently looked at was the coefficient of friction. Now this has 2 things, where one of them is sliding and then the other one is not sliding. So any 2 surfaces will have a unique coefficient of friction. So rubber on asphalt, so tires on the road, will have a certain coefficient of friction, one for sliding and then one for not sliding. And the way that that is related is it depends on the frictional force and the normal force. So our two equations that we generalize from spring constant and coefficient of friction are these. So we said that from the spring lab that it is the force of friction is always the negative of the spring constant times the displacement. So the reason that is, we've got a spring here, and it's hanging, it has a mass hanging from it. So if you look at why these are always opposite, is if you add weight, it stretches this way. So our displacement is down. Well, the spring is pulling up on it. If you did something different and you compress the spring, so instead of hanging a weight on it, let's say that we pushed it together like this. Well, we displaced it this way, and the spring is trying to push against it that way. So no matter what, a spring will always exert the force in the opposite direction of the displacement. For friction, this coefficient of friction, it depends on the surface that's acting on it. And every one is unique. So, like we were saying before, tires on asphalt, or let's say like a piece of wood sliding across a table, all of those are going to have a different coefficient of friction. And the way you find that is by dividing the friction force by the normal force. The reason why we use the normal force instead of something like the object's weight is because if we're on a hill, or if we're holding something up against a wall, then the normal force is not always going to be directly opposite of the weight. So we use normal force because we know it's always perpendicular to the surface here, and that'll tell us about the coefficient. All right, hopefully this helps. Tomorrow we are going to be applying with word problems everything. Goodbye.